Graduate student Mark Yu. He's in the Department of Earth and Planetary Sciences, and he is going to be speaking to us all about monsoons. So, without further ado, Mark, go ahead and tell us about your work.
Thank you for the introduction, Ria. And so my name is Mark Yu, and today I'll be explaining to you about how the monsoons work, focusing on the Asian monsoons. These two are photos of the Asian landmass. You have the Himalayas, and also you have the Maldives, which is actually some tropical islands off the southern coast of India. So a little bit about me. I'm a local, so I grew up in West Windsor most of my life. Grew up in New Jersey most of my life. Went to elementary school in Summit in Providence, but I also moved around most of my life. I'm a fourth-year PhD student in the Department of Earth and Planetary Sciences. Got my undergraduate degree in geology from the University of Rochester before that. So I was actually born in a small farming village in southern China, Hunan province. My family moved to Denmark at the age of 6. And then we moved to the United States when I was 8. And we moved around a little bit after that. So as you can tell, in total, I actually went to 12 different schools between elementary school and the 8th grade. So I moved around a lot, but it did cause a lot of stress growing up, but I've learned to appreciate that because I was able to see different parts of the world and appreciate different views and cultures. So back in high school, my two favorite subjects were history and biology. I didn't really know which one to choose, and so I went to the University of Rochester hoping to double major in history and biology. But it wasn't until I took an elective course for my biology elective called historical geology that I got exposed to what the geological sciences were about. And historical geology basically taught us how the Earth has changed. Earth and biology has changed over time. And I found that was a perfect blend between my two interests, the natural sciences and history. And so I switched over to geology, and I've kept with it ever since. Some of my favorite mineral. So my favorite mineral is calcite, calcium carbonate. And as you can tell from these three images, they're actually the same exact chemical composition, CaCO3. My favorite microfossil is Neoglobocardina durotree, which is a thermocline-dwelling planktonic foraminifera that inhabits the tropical oceans, and it's also made of calcite. The image to our bottom right is the scanning electron microscope image of a calcite. You can tell it's got rhombohedral habit. And the thing with calcite, it's such a powerful mineral because it's very simple, calcium carbonate, but it's very simple. But the chemistry, carbon and the oxygen, reveals so much about how the Earth's environment, temperature, and other conditions have changed in the past. And so for me, it's always been my favorite mineral. So why do I care about monsoons? Going back to where I was born, a small village in China, a farming village, my mother was able to pull up a picture when I was younger. So my grandfather was a rice farmer, and my grandfather before that. So we kind of stayed there for a long time. And with agrarian livelihoods with farmers, you're exposed to the land. And so when I first, instead of having green grass in our front lawn, we had rice paddies. And so growing up, I ran around in the rice paddies. And that's when I figured and appreciated how beautiful nature was. And that's what spurred my interest in the natural sciences. And so, as you can tell from a young age, I was trying to study monsoons because, as I'll explain later, it affects agriculture, society in really profound ways. And it impacts you even more if you're a farmer. So what is a monsoon? A monsoon is the seasonal change in wind direction between the wet and the dry seasons. It comes from the Arabic word Monsoon, which means season. And so these two National Geographic pictures, you see to our right is the winter monsoon, the dry season, and to our left is the winter monsoon during the wet season. you can tell there's a drastic difference, a seasonal difference in precipitation. To our right, the winter monsoon, you can actually tell the direction that the winter monsoon winds blow by the direction that these trees grow. So the seasonally reversing winds and rains are due to difference in heat capacity between the land and the oceans. I'll explain a little later, but the ocean has higher heat capacity than the land. So there are many monsoons throughout the world. Many scientists study them. I focus in on the South Asian monsoon, which is actually a subsystem of the larger Asian monsoon system, which includes the East Asian monsoon. You also have the Austro-Indonesian monsoon. You also have the North African monsoon, South African monsoon, and there's even a monsoon in North America as well. And there's a large South American monsoon. And as you can tell from the annual precipitation plot, these are areas of intense rainfall. And so it's something that's really, really important. In fact, 60% of humanity lives within one of these monsoon systems. So trying to figure out how they changed in the past and how they'll change in the future with anthropogenic climate change is something that scientists have been trying to do. So this is the schematic of how a monsoon occurs. And this represents the summer monsoon. So during the summer monsoon, solar radiation is focused on the northern hemisphere. And so the air over the ocean is cooler than land. This results in the air being more dense and have higher pressure. And so this results in a high pressure cell to develop over the oceans. And then on the contrary, the land heats up much faster than the ocean. It's got lower heat capacity. And this results in warm air rising, resulting in a low pressure. Now, since air likes to move from high pressure to low pressure, you have air flowing from the Indian Ocean to the Asian landmass. And as the air flows, it picks up moisture. This moisture eventually rises and it condenses to form clouds over the Asian landmass. Nucleation eventually occurs, and so the little rain droplets, they precipitate out. And that's what forms intense rainfall over India and much of greater Asia that we see today. So just a short primer on heat capacity, specific capacity. It's an intrinsic physical property of matter, and it basically is defined by the amount of energy, heat, required to raise the temperature of a material by 1 degree. And so as you can tell, water has a much higher heat capacity than land. So I have some numbers that shows that water has much higher heat capacity than we generalize land to be quartz and soil. And that's what results in the differential heating that we see today. The South Asian monsoon, that's the one that affects India, Pakistan, Bangladesh, Nepal, and some other countries, accounts for 80% of the rainfall in India. And it's got heavy implications to agriculture and climate. And that's because the dominant crop grown in much of Asia is rice. Actually, rice is the most important grain for human nutrition. And that 1/5 of the calories being consumed worldwide today come from rice. However, rice is a really intensive and labor intensive, and also requires a lot of rain, a lot of precipitation. And so, as you can tell from this picture, a lot of the rice paddies are irrigated, and they're irrigated through monsoonal precipitation. And so, without the monsoons, we wouldn't have the diverse societies of Asia that we see today. So this figure shows you the reversal of the summer monsoon to our right, in which there's a low pressure cell over the Himalayan plateau, high pressure cell over India, and there's the influx of cool, moist air over the Asian landmass. And then you have to the left the summer monsoon with the blue arrows, and that shows basically wind, the reversal of the wind direction, and wind from India is actually coming from the dry Asian landmass. There's also movement of the ITCZ by the dotted lines. I'll explain to you a little later about what that is. And then with the histogram to our bottom of precipitation, you can see that the most intense rainfall occurs between the months of July and September. And that's when the South Asian monsoon is at its peak. The intertropical convergence zone, or the ITCZ, is where the southeast and the northwest trade winds converge. And it's actually due to shifting of solar radiation being focused during the summer at the Tropic of Cancer, as compared to the winter where solar radiation is focused on the Tropic of Capricorn, which is around 23 degrees south, 23 degrees north. During the summer, the ITCZ moves to its northern position, and moist, cool air flows in from the high pressure regions of the oceans to land. And the ITCZ actually is associated with the rising branch of the Hadley cell, and that's where that's the zone of maximum precipitation. And so as you can tell, monsoons, while they're regional, actually are influenced by global climate dynamics. This is another histogram of Mumbai, India, and you can tell the seasonal intensity of rainfall occurs during June to September. So the rainfall is a blessing for a lot of the people there. Cools the land, irrigates all the crops, and as a result, society functions. A society is able to function, and also the wildlife, and the biota, and the fauna. They all respond in a positive manner. However, there's also when the rains come, if they come at a drastic time or sudden abrupt time, it causes flooding, and that causes damages, and society suffers as well. The summer monsoon, it occurs between April to September, and as you can tell from the figure to our top, it arrives at different times throughout the Asian continent. You can tell in Sri Lanka, it arrives around May 25th, and it eventually moves its way up north before reaching Pakistan during July 15th. Now, this is a generalized map, and it varies actually between the years because how dynamic the climate is. Since it's abrupt and heavy, I mentioned before, it does cause potential flooding damages. And I actually remember growing up, they didn't predict when the monsoons arrived correctly, and it actually flooded my grandparents' entire farm. And so, you know, stuff like this, when you depend on farming as your entire livelihood, when you have intense damage to your crops, it devastates families, and it has ripple effects that go all the way up to, throughout society. Winter monsoons, on the contrary, is when you have winds blowing in from Central Asia that's dry. Depending on some seasons, sometimes of the year, if it lasts too long, it could result in droughts. However, this is a gradual change. It's not as abrupt as the summer monsoon. So this is a NASA video that shows you total rainfall and also the vegetation index. So the main thing I want to show you is around when peak monsoon occurs, you have intense monsoonal rains, and then there's the greening, or the greening of the Asian landmass. That's directly due to precipitation. And so as you can tell, precipitation and the monsoon play a really, really drastic role in regulating how the ecosystems of the world responds. So now going into the fun part, this is how we study them. So as a geochemist, I love to make measurements. These are some photos of when I was at ISOCamp at the University of Utah, in which we use machines called mass spectrometers, and we separate isotopes based on the mass to figure out how climate conditions have changed in the past. And before we do that, though, we have to retrieve or find our archives. Archives are basically just like you would in a museum or a library. Geologists, we need to read into the past. So we use these archives They include, coral speleothems, cave speleothems, corals, marine sediments, lake sediments, terrestrial sediments, and even ice cores and tree rings. And then there's also atmospheric models that will predict how monsoons will change in the future and also tell us about how they changed in the past. And so if you couple these measurements, these proxies with atmospheric models, we have really strong tie points as to figuring out how climate will change. So I'm going to go through some of the archives that we use real quick. There's coral records. Corals are basically aragonitic organisms that secrete aragonite for their exoskeleton. And there's people who go around the oceans, who dive into the oceans, core into these corals. And then from this, you can retrieve nice slabs that we cut. And the really important thing about corals is that they grow annually. And so there's bands that grow annually. And each annual band records the seasonal variation in sea surface temperature and precipitation of the waters that surround it. And so corals are really strong in that they're able to provide us monthly high-resolution records of how temperature, precipitation has changed in the past. So to our top left actually is a hole that's cored. And so scientists, this does not kill the coral. Scientists actually fill it up with concrete. And then since it's only the outermost layer that's growing, after a year or two, the outermost layer will be fully plugged, and the coral will be growing over it. And most people don't think of ice cores when we think about the tropics and where the monsoons are. But actually, the Himalayan plateau contains some massive glaciers that people have taken advantage of, cored into ice cores. And so to our bottom right is actually Dr. Lonnie Thompson from Ohio State's Bird, Polar, and Climate Research Center, in which he's led multiple expeditions to the Himalayan plateau to core into the glaciers. And with that, we can record, we can decipher how precipitation has changed, how temperature has changed in the Himalayas. So the Himalayas are the heart of where most of the Asian rivers are. Learning from my history class back when I was a history major, whoever controls Tibet controls a lot of Asia, because all the rivers, the Yangtze, the Brahmaputra, the Indus, and the Mekong, they all originate from the Tibetan plateau due to the monsoonal rainfall. And so people have taken advantage of this and have attempted successfully to core and decipher what's in the ice cores. Just like tree rings and coral records, every year when it snows, it forms a new band after compaction on the ice cores. And so you have banded layers that tell us how conditions in the Himalayas have changed over time, without we can reconstruct how monsoons have changed. One thing I want to note is that the glaciers are getting smaller with anthropogenic climate change. Lost a lot of mass with glaciers, and so it's a really vital time for scientists to retrieve what we can with the alpine glaciers. Cave records are also important as well. So because a lot of the tropical caves, they're inundated by monsoonal precipitation. The rain eventually seeps into these caves, and they help form the limestone features that we see here. So if it grows from the bottom, it's called a stalactite. If it grows from the top, if it grows from the bottom, it's a stalagmite. If it grows from the top, it's a stalactite. And just like everything else that has bands, we can retrieve these archives, split them, and also do high-resolution measurements on the geochemistry of these corals, of these cave records, stalactites, to figure out how the precipitation patterns have changed. Other terrestrial records include tree rings, which we can look at the deuterium isotope to figure out how precipitation has changed. There's also people who study loss, which is basically compact silt-sized sediments. That's aeolian or wind-derived. It originates from the plateaus of Central Asia. And from that, we can determine wind strength, wind direction of the monsoons, associated with the monsoons. So people do stratigraphy on these, in which they look at the different layers, the different bandings, and they can decipher how monsoonal intensity has changed over time. And then there's people who core into the oceans and who core into the lakes. And so the bottom figure is actually from Peru, in which there's an expedition to core into one of the lakes. And then from the lakes, it can reveal seasonal variations, upwelling, wind strength, and in sea surface, and in temperatures. And so as you can tell, there's many terrestrial archives that scientists look into to decipher how climate has changed in the past. Now, this is what I love. I'm a marine geologist who likes to look at the geochemistry and the micropaleontology of the fossils that inhabit the water column. And so to our right, figure of the blue boat, Geordi's Resolution, which is part of International Ocean Discovery Program. Rutgers has a strong presence in. And last fall, summer, I had the fortune of actually sailing on one of the Geordi's Resolution expeditions off the Chilean margin. So I was a sedimentologist in which I described the sediments as the boat was drilling them. And from that, we can retrieve records that span thousands and millions of years. So that's the advantage of the marine sediments. Marine sediments can go a lot deeper in time as compared to some of the terrestrial records, as compared to corals. Corals, their advantage is that since they grow annually, you get high resolution annual measurements as compared to deep marine sediments. You know, the sedimentation rate at the bottom of the ocean averages 1 centimeter for every 1,000 years. And so, because we require a lot of 4AMs to run our samples to decipher our signals, we can only our resolution, our temporal resolution, isn't as high compared to corals and tree rings. But we can look a lot further back in time. And so, actually, that image of me looking at the microscope, I'm actually trying to pick out the different foraminifera species. So foraminifera are single-celled calcareous protists that inhabit the water column. And they inhabit various parts of the water column, from your upper layer to your thermocline to your bottom waters. And so I'm picking out the individual species so I can do chemical measurement on them to figure out how the water column has changed over time. That has implications for the strength of the monsoons and larger teleconnections with other parts of the ocean. So this is, I'm going to show you a video codes of what I was doing on the Geordi's Resolution. So Lauren Adamo already went into, Dr. Lauren Adamo went into a lot of this with how we get cores and what we can tell from the cores. But as you can tell, I was a sedimentologist, so we were continuously trying to describe the cores, doing physical property measurements, making thin sections, and also running it through a magnetometer to figure out paleomagnetic intensity. And so there's a lot that marine geologists undergo, retrieve these samples, and we can decipher a lot as to how the Earth has changed over time, because oceans are one of the largest reservoirs of carbon and other elements. And this picture is from NASA, and it shows you basically Earth at night. And the main thing I want you guys to take away from this is that the Earth is, we're all in this together. The one caveat I like to point out is light is usually associated with how developed the nation is. So a lot of the developing nations don't have that much access to electricity and energy. But you can tell a lot of Asia lights up at night. And so that shows you why 60% of the world's populace lives within a monsoonal system. Monsoons are really, really important to the agriculture society. It's really important to figure out study them. So these are some things that young scientists can do in the future. We, including me, we can endeavor to produce high resolution, long-term records, geochemical records, statewide scope records. There's also a connection between the monsoons and El Nino. During an El Nino, the summer monsoon is actually drier over India. But then there's other connections with the Indian Ocean dipole and extratropical connections that paleoclimate scientists haven't figured out. So these are things that we're trying to push towards in the future. We're always trying to form more accurate models as to how climate has changed in the past and how it will change in the future. So my one take-home message is that all the young scientists out there, geoscience is really important. Study your fundamental sciences, biology, chemistry, and physics, but also know that you can apply the knowledge that you learn in sciences to the geosciences, solve complex and societally relevant questions to climate and our resources. And so that's all I have for today. I'll show you a video of the Patagonia ice sheets, the Patagonia fjords, when I was off the coast of Chile, and answer some questions. Okay, so I'll start with question number one. Has the dam building in China affected monsoon damage in Southeast Asia? So this is a rather political question. I remember learning about it, in which, especially the Mekong River originates in China, but if you dam it, and China has been proposing to dam some of the parts of the Mekong that they own, and it definitely will affect the amount of water that Vietnam, Thailand receives, and so it is. Does it affect monsoon damage? Dams are good in that they can regulate how much flooding occurs downstream, and so dams are actually helping with monsoon and abrupt monsoon flooding. But you do have to regulate how much water is coming downstream. Are there winter monsoons anywhere else besides Central Asia? Yes, there are. So just like how winter monsoons and summer monsoons occur in India and in Central Asia, there's always a preceding winter monsoon after the summer monsoon in all the global monsoons that we see. So this includes the African monsoons, Austro-Indian, Indonesian monsoons, and even our American monsoons in Arizona. Leah's mom would like to know, are there warning systems in developing countries before cyclone hits, and how often are they updated? There are, I believe, just as how NOAA and NASA produces these global maps as to how hurricane is developing. I know in China they have a similar phenomenon with the typhoons, and meteorologists are investigating this, and they have good clues as to when a typhoon or a cyclone will hit. Now, a lot of this causes the most damage with developed nations, and so it's a matter of is this information being relayed to effectively going to be effective? But yes, science is a global effort, so there's a lot of lot of bright scientists trying to warn people as to how cyclones are developing. How can you study monsoons through microfossils? So this is a very interesting question. So, like I said, each microfossil inhabits a different part of the water column. Now, monsoons have changed over time in intensity in thousands of years, timescales. And so from this, I can figure out how sea surface temperatures have changed, how nutrients have changed, and how upwelling has changed. That's recorded in the microfossils. And because the microfossils, they live in equilibrium with the water surrounding seawater, it can record a lot of the chemistry, a lot of the chemical parameters. And these physiochemical parameters are directly impacted by the monsoons. And so these microfossils are giving us windows as to how the monsoon changed in the past. So once I figured that out, I was blown away and I was fully hooked onto my PhD. And so it's a really, really strong, powerful tool in microfossils, the forming itself. Another question, what is the effect that global warming has in the monsoon? Could the timeline, April to September, be shifted? Yes. Can they last longer, or will the monsoon system be predicted to be shorter? So these are all really good questions. These are questions that our scientists are asking today. So has global warming affected the monsoons? And my response is yes. If you listen to Dr. Ken Miller's talk, Dr. Ken Miller actually mentioned that with the global reports on climate change, the areas that are getting wetter will only become wetter. The areas that are becoming drier will unfortunately be drier. And so the monsoon system, because the general trend is that because they are wetter, the summer monsoons will be stronger. Now, like, remember how I mentioned there's effects with El Nino, Indian Ocean dipole, and other climatic effects? These affect the duration, the intensity, the timing of the monsoons. And so these are all really important questions that scientists are asking me today. Unfortunately, I can't give you an exact answer because I don't study common era monsoons, but yes, they are changing in intensity and in duration. Something that we really need to tie down for future predictions. Which proxies are most reliable for studying monsoons? Okay, so let me describe what a proxy is. So a proxy, I love that term whenever I hear it. A proxy is basically a window to the past, indirect measurement. Okay, so there's many proxies that we use. The stable isotope measurements of the foraminifera, deuterium, leaf waxes. There's many. But which one is most reliable for studying monsoons? I would go with one of the proxies that measure precipitation. So deuterium. That's the hydrogen isotope. And I would say you get that out of leaf waxes, you get that out of the tree rings. And I would say deuterium might be one of the stronger ones to study monsoons. Okay, so the other question is coral drilling safe for the coral? And the short answer is yes. The corals themselves don't die from drilling. You make a small enough hole. Remember, only the outermost layer is growing. And so if you're making a hole that's a couple of inches, that's not going to kill the coral, because we always plug the hole with concrete, and then it can grow another layer. A surrounding layer can grow on top of it, and so it doesn't kill the coral, which is really good. Speleothems and the cave records, though, on the other hand, once you take them out, they don't grow ever again. So those are things to keep in mind. And yes, it is in terms of environmental conservation, it is a question that we need to ask. How did the Himalayas affect the monsoons? Okay, the Himalayas. So I can answer this with so how did the Himalayas influence the monsoon season? That's the question. So I can answer this with a geological perspective, in that without the formation of the Himalayas, the uplift, we wouldn't have the intense monsoon that we see today. Now, when did the Himalayas occur? When did that uplift occur? That's when India hit Asia billions of years ago. So, how do they influence the monsoon seasons directly? Is that it's a landmass and it heats up much faster during the summers. Moist air from the ocean rises and it causes condensation and precipitation. So that's the short answer. Now, it also during the winter monsoons, the Himalayas also block a lot of the air that's coming from Central Asia and Northeast Asia. So that's why a lot of the winter monsoon rains, or a lot of the winter monsoons are dry in India. And so, yeah, the Himalayas is basically a barrier for the monsoons. It also causes precipitation. Are supercyclonic events like AMP, AMFAM going to be more common in the future because of climate change? The question is, are supercyclonic events going to be more common in the future because of climate change? And so that goes back to the cyclone question. Yes. So I'm not a climate scientist. Still a geologist. I'm trying to study more about atmospheric science. But if you recall from Dr. Ken Miller's lecture or his answers, frequency, it has to be questions with frequency and duration, and also intensity. I think the intensities are going to increase, but frequencies, that's an unknown. But obviously, I'm not a climate scientist or an atmospheric scientist, so I would defer that question. Where are the cores you are working with for your research located? That's a very neat question. So my samples are actually from the Maldives. So this is a carbonate platform in the central Indian Ocean. And basically what happened was back in 2015, my advisor, Dr. James Wright, he sailed on a global expedition, IODP Expedition 359, Maldives monsoon and sea level, and they cored into the atolls of the Maldives, retrieved long sediment cores, brought them back, and they're currently being stored in the Texas A&M Core Repository. And what we did back in 2016 was we sampled high resolution layer, brought them back, and I've been running the geochemistry on the formula for ever since, from the Maldives. And that region is very interesting because it could be potentially influenced by multiple climatic events from the Arabian Sea to the Indo-Pacific warm pool to the monsoons to the north. So it's actually a very interesting location for me to study, and that's what my dissertation is on. Another question: when did the Asian monsoon begin, and how different is it now? This is a tricky question. So one thing I would like to say is that I know the South Asian monsoon intensified at 12.9 million. 12.9 million years of intensification. Now, when did they begin? This is a question that we have to look into the paleoclimatic record, and I would say millions of years ago. Millions. There was a proto-monsoon during the Miocene, so like in the 20 million year range. There was a proto-monsoon there. And before that, there's speculation as to whether there was a strong monsoon. And so I would push it back to Miocene, sometime 20 couple million years ago. And how different is it now? It wasn't as strong, the intensity, and the duration wasn't as continuous. As compared to today, it's you kind of know that there's a seasonal variation, and you kind of know that it's going to occur. Now, when and how strong and all those other questions are further questions that we need to address, but we know it's occurring now. The Asian monsoon also, a lot of it has to do with the Tethys Sea, the closure of the Tethys, which is actually an ocean that separated Europe from Asia. And once all that closed, once plate tectonics drove them all together, that's when we see the modern Asian monsoon today. So this is a really good geological question. But like I said, probably 20 something million years ago. Okay, Carol Drews would like to know, do we have monsoons in North America? And if we have them in the US, how are they studied? So this is actually a really good question. There's monsoons from that map that I showed. Um, there's actually a monsoon, as you can tell, in actually it's denoted in Florida and also in Arizona and Mexico. So that's where the North American monsoons are. And how do we study them? So there's people who study the vegetation, the tree rings, the sediments of the Arizona monsoon. So you can basically take a slab of a tree, and from that you can look at the different bands, pick out the different bands, and each band is an annual year. And from that you can get a geochemical measurement from that deuterium. You figure out how precipitation sources, precipitation strengths have changed over time. So I'd say tree rings are a good way to study the North American market. Lauren Barron would like to know, do hurricanes affect monsoon patterns? Oh, you guys are asking very good questions. So hurricanes, by definition, occur in the Atlantic. Monsoons occur for the most part in other parts of the world. Now, my specialty is not in the North African monsoon or the South American monsoon, but I'm sure there is some connection between hurricanes and monsoons. And I'm not a climate scientist, so I can't explain to you how hurricanes affect monsoons directly, other than it forms intense precipitation during a hurricane. Now, how the hurricane season is also something that needs to be factored in. That's during the summer months. And so, yeah, this is a question that's outside of my comfort zone because I focus in on the Indian Ocean. But I would say yes, but I defer this question to someone who studies hurricanes. We have many great people who study hurricanes in our geoscience in our department that I would direct you towards. Where else on Earth would you look for a monsoonal record? And so I mentioned most of the big ones, right? You have a lot of terrestrial records. You have a lot of terrestrial records, the cave records. You have your lost records. You have your tree rings, ice cores, and then you have your marine records, the deep sea sediments, corals. Where else would I look? Those are the big ones, I would say. Actually, another thing you would do is you really want to figure out how climate affects society. As a historian, you can look back into the tax records. How much the ruling class was able to tax people. More taxes would usually indicate a more bountiful harvest. So a stronger, wetter monsoon. Maybe something like that. Or you could even archaeology. You could look at the archaeological record to see if strong monsoons causing flooding. So yes, I'm giving you options that's outside of the geology. That's more archaeology, history. Can you see any other weather related to events in the geologic record? Wow, you guys are asking really good questions. Yes, the short answer is yes. There's people who study, they're called paleotempests, paleotempestology. Actually, we have Ben Horton, Dr. Ben Horton, and then there's Kristen Joyce from our geology department. She studies paleotempestology. Bob Kopp. So what they do is they try to figure out when the most intense hurricanes are. Other weather events, Indian Ocean dipole. We will study that. The Pacific Ocean dipole. El Nino is a big one. El Nino, so that's basically shifting of the thermocline depth, and that causes either intense rainfall over Peru or less intense precipitation over Peru and South America in general. So there are people who study those climates. So those are the tropical climates that I know of. Those are the ones that I know of, but sure, there's many other scientists who study, wildfires, typhoons, and also there's many sorts of weather patterns that you can study. Yes. So can you see any other? Oh no. So Carol Drew asks, are the Amazon rainforest fires being affected by the monsoons? Well, again, this is I don't specialize in the South American monsoon, so I don't know too much about it. But we do see from the news that there's more and more wildfires occurring throughout the world. Now that's a question as to I would answer that with a question as to is South America becoming drier and drier? Are the Amazon rainforests getting drier and drier? And I would defer that question actually to Kaio from our geology department, who's a PhD student who actually studies a lot of the ecohydrology in the Amazon. So I pumped that question as well. Why did you end up studying oceans, corals, and monsoons? Well, I can give you the short answer or the long answer, but the short answer is after my undergrad at the University of Rochester, so I studied, actually my major was geological sciences. I had two minors, one in history, one in biology, another one in environmental geology courses. So I was finishing up my undergrad, and for a long time I wanted to become an economic geologist, extraction of natural resources. But then I was applying to graduate school. I wanted to study sedimentary geochemistry, and I was fortunate enough to end up to be provided an opportunity to study at Rutgers, to study IODP, or the International Ocean Discovery Program in the Maldives course. And so it kind of was luck, fortuitous luck, that ended up in this project. A lot of now that I look at my life's trajectory or what places I've gone to, a lot of it was luck. A lot of it was timing. I wasn't coming out of undergrad. I wasn't dead set on studying climate. I never took an oceanography class back in undergrad, but once I came to Rutgers, where we have a strong marine science program, Department of Marine and Coastal Sciences, once I started taking classes like chemical oceanography, geology, even physical oceanography, I realized, wow, the oceans are as dynamic as land. I used to think that the ocean was just wet and blue, but there's a lot more occurring underneath the waves than meets the eye. So I fell in love with that project and I've been working on it ever since. But the short answer is why. Why did I study geology? So this is a question that goes back. I was on the evolutionary biology track. One of the electives was historical geology. And coming from the New Jersey high school curriculum, I was told to study biology, chemistry, and then physics, and then do 1 year APs as senior. Environmental science, oceanography, those are ancillary sciences. But no, once I started studying geology, I realized geology incorporates a lot of the things I studied in biology, chemistry, and physics. It's an applied geology. There's also people who study the tectonics, ore deposits, minerals, natural resources. Geology is actually a really useful science discipline for us to study how the Earth directly affects society. So I found it the most relevant science for me to study in order to advance humanity. Lastly, where have you traveled in your studies? So, as a geologist, we're blessed with many opportunities to travel the world. So in terms of where I've gone for just geology, we do a thing called undergraduate field camp. And so I went to Nevada, Reno, Nevada for field camp. Gone to Utah, gone to Wyoming. I've gone to Yellowstone, all the major parts of the West. Gone to the Bahamas, and then for my 2 expeditions, I was actually in Uruguay, and so we departed from Montevideo, and we did coring and seismics off the coast of Argentina. So I've been there, spent 50 days there, and then I was also off the coast of Chile. So we were in Punta Arenas, which is the southernmost major city in South America, which I saw some of the most beautiful fjords and natural landscapes that I could hope for. So I'm really fortunate to have fell into geological sciences because it's a degree in which we can travel the world and do lots of interesting science to solve a lot of complex questions that's really relevant to society today. Okay, I think that's it for today. I guess that's all we have.
Okay, thank you so much, Mark, and thank you for everyone who tuned in today. So be sure to check out our talk next Thursday on May 28th. We will have Michael Sprague, a graduate student from Loma Linda University in California, speaking to us about pterosaurs. So be sure to check that out on Thursday at 2 p.m. And thank you again, Mark, and I hope everyone enjoys the rest of the day.